I want to do 79 because it's kind of a good overview of the whole module. And we're going to move on to module 5 today. So there's a lot of good things to talk about in number 79. So they gave you this information that at time 0, the normal height of the river is 8. And then there's a flood. So 4 hours later, the height is at 14. And so if this is exponential growth, right away, you could say, oh, I know what I can get really easily. And it's really important to get started. So I've got an increase in hours of 4 hours. So what can I easily calculate it to get started?
4 hours.
He said the 4-hour growth factor. Yeah, G. Okay, good. So 14 divided by 8 would be the number that you would multiply 8 by to get 14. And we know that's a growth factor. Multiplying by the current output to get the next output 4 hours later. So that would be the 4-hour growth factor. Cool. All right, so it's 14. 1.75 is our 4-hour growth factor. Okay, what's the percent increase every 4 hours? 75% increase every 4 hours. Okay, so to get the percent increase every hour, I'm going to divide 75 by 4. Lots of no's over here. What about this side? No, percent increase is not directly transferable, right? Because you get a compounding effect on percent increase. So what is directly transferable? Growth factors. So we got our 4-hour growth factor. So we want to start by getting the 1-hour growth factor, which is? So the 1-hour growth factor. Take the 4-hour growth factor and? Why? Because this number, multiplied together 4 times, gives us that. So that will be our 1-hour growth factor. $1.15. So what's the 1-hour percent increase? 15%. So that was part A. The hourly growth factors are 1.15, which means an increase of 15% per hour. Okay, so 15% per hour, that's our hourly percent increase. Okay, so we can write the function f, this is part B, as a function of h. Initial value of depth, 8 at a equals 0, times the 1-hour growth factor, to the h. Doing okay? Is that right? All right, now we want to rewrite that in our exponential form. Or, sorry, that is exponential form. In our continuous exponential form. Which means the h stays the same. And we know that our b is e to the k or e to the r. They're using k here. So e to the k. So that would be our continuous form. It gives the exact same output for the same input. It's the same exact function, it's just a different form. Okay, it's just a different form. And this is in the kind of through the perspective of continuous rate, right? K is the continuous rate. So to get that continuous rate, we take 1.15 equals e to the k. And now we're asking, how can we get that value? It's an exponent. So we have the tool now to rewrite that as a log, right? In this case, since it's the exponent of e, we have a special log that gets us exponents of e, which is? Natural log is the exponent of e that will give 1.15. The exponent of e that gives 1.15, that's a natural log. Point 1.4. Okay? So the continuous rate, this is k. So the continuous rate is what percent increase? 14 or 13.98%. So every hour, the height of the river is increasing 13.98%, right? Because that's the continuous hourly rate. So every hour, ln of 1.15. Yeah. So I rounded it here, and then I went back to, when I changed the percent, I got more accurate. So this is the percent increase of the height of the river every hour, 13.98%, right? Is that right? No, the continuous rate is not the true percent change. We said it last week a couple times, or lots of times. You got to get this. This has got to sink in. The continuous rate is not the true percent change. This e to the k thing, this k, not the true percent change. Watch the videos. We said it many times. But that continuous rate, so what is the true percent change? 15%. Okay, so these numbers as just values are different, but they represent the exact same exponential growth. How is that? They're different values, but they represent the exact same exponential growth. How is that possible? How do we make sense of that? Do you remember? Which one's the true percent change? 15. So if that's equivalent to a continuous rate of 13.98, what is this number about? Anyone want to give it a shot?
That's the rate it multiplies by every instant.
Okay, kind of. We divide by. We have to divide it up first, and so yeah. So it's you have to combine this with continuous compounding. You take that percent, you divide it up into a zillion chunks, and we find that percent increase every moment. And then we let the percent increase build on itself over the course of an hour. Will really truly result in a 15% increase. It's like APR versus APY. So this has to be combined with, so this number combined with the moment-by-moment continuous compounding results in, after 1 hour, a true percent change of 15%. Keep practicing that. This is hard. This is a hard thing for students to grasp and remember. Okay, so that's why we're repeating it. So that's part D. What's the value of k represent? It represents the continuous rate that, when combined with the moment-by-moment compounding, results in an hourly increase of 15%. Does it make sense now? Can you remember that? Remember that. So again, these problems in the exam relating to continuous rate, low success, because it's like it doesn't stick. So you got to keep practicing in these problems, talking through what does the continuous rate mean? What does the value of B mean? What's the true percent increase? How do those numbers fit together?
I got a question.
Sure.
For k, if it's negative, that means it's decreasing?
DK, that's right, DK. Yeah, so when your k is greater than 0, like this one, you have increase. When k is less than 0, yeah, so let's write that down. When k is greater than 0, B is greater than 1. B greater than 1 means increase, right? Then k will be greater than 0, meaning this is like a rate, the continuous rate. When k is less than 0, what's B? Between 0 and 1. That's our DK, right? That's the portion that we keep when we multiply. We multiply by B to get the portion that we keep. That will result in a negative percent change or negative continuous rate. Other questions? Yes, sir?
If you were given the continuous rate, you had to find the growth
That's even easier, right? So let's do that. Let's say the continuous rate. Let's do a decay. The continuous rate is negative 13.5%. So what do you want to do now?
Would you have E and you just put in the decimal?
Would be negative.
0.135.
That's right. All right, let's find that. That would be B. And we're expecting that to be between 0 and 1. E to the negative 0.135. 0.874. So what is that? That's B. And what does that represent in the problem? The decay factor, which is what portion? Is it is it what we lose or what we keep? What we keep. We always take 87.4% of what we have every unit of whatever the input is. Okay, so what's the true percent decrease? Yeah, it's going to be 100 minus 87. Is that 12.6? Yeah, you could say 12.6% decrease. I was going to write decrease here, or negative 12.6. But anyway, these are the numbers we're comparing, right? The continuous rate of negative 13.5 and the true rate of decrease of 12.6. So that little exercise I did right there, can you do that and make sense of everything along the way? It's really important. Why is it different? Because that 13.5% has to be combined with the moment-by-moment compounding, resulting in a true decrease of 12.6%. Does that answer it?
Yeah.
Cool. Yeah, so given the continuous rate, to find the growth factor, that's easy. It's just e to the k, right? So this is it's also easy to find the continuous rate, but you got to apply log. You got to apply log if you know the growth factor and you're solving for the continuous rate. Okay, other questions? All right, we're going to start Module 5. We're going to talk about covariation, but really we've been talking about this thing covariation the whole semester. It wouldn't be wrong to say that all of pre-calculus is really about this one thing, covariation. So, what is it? What is that covariation? What are we talking about? And actually, you put this in Microsoft Word, you'll get a little red line underneath. It says, oh, that's misspelled because it doesn't recognize that word. But for us, we should understand based on what that word is. What does it mean? Covariation. Any ideas? All right. All right. So I think you mean quantity, right? Yeah. So we talked about at the beginning of the semester. We talked all about quantities and variables to represent quantities, and so it's basically right. It's about one quantity varies, and we have another quantity. As that one varies, the other quantity varies with it. So how two quantities change together? So our whole course thus far has been about covariation. We didn't really talk specifically about just proportionality of quantities, but this is a good place to start. So if you have these two quantities represented by the variables x and y, if you have a proportional covariation, then the value of y to the value of x is always constant. Okay, the next one, so what we did in depth, we spent several weeks, was constant rate of change. What remains constant for constant rate of change? So if you've got these two quantities, y and x, what was constant if those vary with constant rate of change? Yeah, what was k? K is the constant. The ratio of, not y to x, right? Some of you are saying it, change in y to the change in x. That was our whole point of constant rate of change. Changes in y maintain the same size relative to changes in x, and that's that ratio. And then we formed from that, we formed the point slope form of a line. Okay, and then from constant rate of change, we moved on to, talked a lot about functions, and then we did exponential growth. Exponential growth, what ratio? We have a constant ratio in exponential growth too. What constant ratio do we have with exponential growth? What was exponential growth all about? What was the kingpin, the centerpiece of exponential growth? Yeah, the growth factor. How is the growth factor a constant ratio?
Changes by that same growth factor per unit of time.
Right. So how can we write it as a constant ratio, that growth factor? How did we find the growth factor on the last problem? We had zero, at 0 it was 8, and at 4 it was 14, right? What stays constant? How did we get that growth factor? 14 divided by 8. So it's the next output divided by the current output is that constant growth factor, right? So there's many, many different ways that two quantities can change together. Here's just 3 examples. And we've spent a lot of time talking about constant rate of change and exponential growth. So now we want to look at it a little bit differently. We want to just look at, given any 2 quantities, can we kind of model or create a graph for how they change together? So now we're kind of taking the numbers out of it. We're taking the actual values away, and we don't really care at this point. We don't really care about, is it exponential growth, is it quadratic growth, is it constant rate of change. We're more interested in creating a general graph for any 2 quantities that we're as we monitor the situation. Okay, so there's kind of 2 parts to it. The first part is identify which quantity is considered independent. Usually call that x, the x quantity, or on the horizontal axis, and which quantity is dependent, which will be a vertical axis. So we can't create a graph unless we know exactly where the quantities are going. Okay, that's our first thing. And then the second step would be where the actual analysis comes in. We're going to consider small equal increases of x, or the independent, one at a time. For each of those increments of x, we're going to answer 3 questions. Okay, so this for many of you may be something you've never done anything like this before. Okay, so you kind of have to memorize this kind of set of steps. All right, so that it becomes more natural as you practice it. But at first, your instincts are going to take you in another direction. Try to be deliberate about kind of following this way of thinking, and it'll help you to have accurate thinking, okay? The first thing is, as x increases, so as we have a change in x, it's a simple question, it's just the easiest one. What does y do? Does y increase? Does it increase a lot? Does it decrease? Does it stay the same? So that's kind of the starting point, and that's easy, hopefully. So as x increases, how does y change? Does it increase? Does it decrease? And in general, by a lot or by a little? All right, the next thing is, as x increases, how does the current change in y, whether that's an increase or a decrease, how does it compare to the previous change in y? So now we're comparing changes. This is the key right here, comparing changes. So in other words, what we're saying is, how does the change in y change? Okay? And then from that, naturally comes the rate of change. The rate of change comes from how the changes are changing, how the changes change over these increments of delta x. But we're going to focus the most on, so this just is natural. This naturally flows out of B. So we're going to focus our emphasis on B to really understand that, figuring out what the change in y is for each increase in x, and then how do those changes compare? What is the change doing from increment of x to increment of x? Okay, anybody have a question? So we're going to do some examples. So I really encourage you, try to, you may look at these situations and be like, oh, I know what's going on, and just kind of using your own intuition. This is a really good skill to practice. So pretend that this is your only avenue for solving these problems, and work on this, okay? Because it's when students generalize too fast, you quickly make conclusions and you don't go through this kind of step by step, that's when you run into error, okay? And your reasoning gets confusing, okay? So practice this. So the first one we want to look at is, you've got a graph for it, page 183. So this is Module 5, Investigation 1. So you imagine a bottle given below. Imagine filling the bottle with water. Make a possible rough sketch of the graph of height in the water, and the bottle as a function of the volume in water. So we want the height of water in the bottle as a function of volume. And we're going to follow our step by step. Don't rush into the final graph, because when the examples get harder, you want to have this kind of system down so you can analyze harder situations than this. So the first thing is we got to determine what's the independent quantity and what's the dependent quantity. So what's independent and what's dependent? Is the independent quantity height or volume? I heard both. Our independent quantity is what we're going to put, like it's like x, what we're going to put in the horizontal axis. So this is our independent quantity. Question?
Wouldn't the volume of the container depend upon the height of the container?
It's the volume of water in the container. Yeah, so this volume of water in the container and then the resulting height. And so, but you're right. The height depends on the volume in the container. So they practically told us. All we had to know is that independent is going to be on our horizontal axis, dependent then we show on the vertical. So what do? We consider small equal increments of which? Height or volume? Volume. We're going to take small equal increments of our independent variable. We're going to march across exactly the same amount of volume every time. So this grid makes it nice. So we can just call this, say, like 10 milliliters or something. Small, that's a very small amount. 10 milliliters at a time. So we're going to take our first 10 milliliters. We can show that with a horizontal, like delta V. So it's like delta V1. So as V increases from 0 to 10 milliliters, first question is, what does the height do? Increase, decrease, stay the same? It increases. Better increase, right? So as we put some volume in there, the height's going to increase. All right? And so then a lot or little? Just a little bit. Imagine 10 milliliters in a chemistry flask, right? It's just a little bit of increase there. We don't care about the numbers. We're just analyzing the changes. So that gives us a point. Okay, so we got delta V1, resulting delta H1. We get a point on the graph. It's 0, we got 0, 0, right? 0, 0. Okay, take another, so we can't compare any changes yet because we only have one change. So we move on to the next change, and we say, add 10 more milliliters, delta V2. Just like that. First question, does the height decrease, stay the same, or increase? It increases, okay? So we're going to increase in height. This next increase in height, now this is question 2. How does it compare to the previous change in height? Is it the same, less, or greater? Why greater? Yeah, as we go up a little bit, so now that it got narrower, so for the same amount of volume, we're going to see a greater change in height because it's narrower. So maybe like this. I know, so if this feels easy, that's okay. Just still practice it, because when it gets harder, you're going to just harder examples in the homework. You need this method to really make sense of it. If you generalize and make conclusions too fast, that's when you run into difficulty on harder problems, okay? Next one. Same, we got our delta V3, 10 milliliters, same amount. When we add that little amount of volume, does the height increase, decrease, or stay the same? It's going to increase. This third amount of increase, how does it compare to the second change in height? So this third change in height, is it more, less, or the same than the previous? More. Because it continues to get narrower. So this is going to be a greater change than before. Gives us another point. Let's do it one more time. Oh, I hate that. Thank you. Okay. One more time. Add 10 milliliters. This is delta V4, fourth change in volume. Will the height increase or decrease? Increase. This change in height, is it greater or less than the previous change in height? Greater again. Gives us a point. Okay? So now we've done 4 changes in volume. We've looked at the 4 resulting changes in height. Now this may be enough to generalize. Okay? So what is happening to the changes in height for equal changes in volume? So we got delta H1 right there. Here's delta H2, delta H3, delta H4. So in a general sense, what's happening to the change in height for equal increases in volume? The change in height is? So just because it's a curve, does it mean it's exponential? Exponential growth is a very, very specific type of covariation. There's lots of curves in the world that are not exponential. Okay? There's lots and lots of curves, graphs of curves, that are all kinds of different things besides exponential. So we're not interested in that right now. We're just interested in the resulting graph, right? What that resulting graph is. So you told me the changes are increasing. Is that right? And so, is this constant rate of change? No, because constant rate of change, we said equal changes in volume would result in consistent changes in height. That was one of our definitions for constant rate of change. We don't have consistent changes in height. We have increasing changes in height. And constant rate of change was what kind of graph? Straight line. So this is not. So we got increasing changes of height. Means, what about the rate of change of height? So increasing changes of height. And now we're on question 3. So we really focused on question 2, comparing the changes. What about the rate of change of height? Therefore, well, it's not constant, you said. What is it doing? What's the rate of change doing? Increasing, right? Down here, it's a lesser rate because you get less of an increase in height for the same change in volume. Later on, same change in volume gives you greater changes in height, so that rate of change is increasing. And so what does the resulting graph then? It's not linear, it bends up with that rate, right? So the rate starts at a certain amount, but then those changes are greater, so then it makes it bend up or curve up. So this is called, when the rate of change is increasing, that's called concave up. Which means curved, right? Curved upward. And that concave up represents the rate of change increasing. Okay, so if that feels easy, good. But again, I really encourage you, practice this very methodical, taking equal small changes of your independent, analyzing the resulting changes of the dependent. Okay, there's a skateboarding example. Skateboarding in a half pipe. If you don't do this, and you just try to make a conclusion, you're going to get it wrong, okay? You got to do this. And there's other examples too. Okay, so let's, we're going to switch it now. Can I take this off? Any questions? So now we're going to switch it up here, and you're going to look in the homework. Yeah, so let's do, how about, you could do number 1. And so it's, for number 1, you're creating the graph of height dependent on volume the same way we just did. So you can kind of ignore these instructions should somewhat match what we did, but focus on what we did to see. Yeah, so they're just asking a very broad question. So you can, it's similar, but it's much broader. So take my very specific steps, my instructions, the 1, 2, and 3, and apply it to the spherical fishbowl. And then I want you to do this, 4C. This is the other way around now, but you're still going to do the same thing. You're going to look at equal changes in volume and analyze the resulting changes in height, and then you're going to draw the bottom. So it's going the other way, but it's the same. You apply the same method to do it. So do number 1. We're going to sketch the graph of the fishbowl, of the height of the water of the fishbowl, and then part C, is this number 4? What's this? 4C, where you're going to do the same analysis, increment by increment, and then draw the bottle as a result. Okay, and you do that while I take roll, okay? Yeah. No, I'm more interested in analyzing with the small changes and drawing the bottle. Is that you talking about this one? actually 3 parts to this bottle in part C. So to here, this first part, and then here, and then this whole part. So this is like part A, part B, and part C of the bottle. So in part A, I add a little water, I get an increase in height. I add the same amount of water again. How does the new increase in height compare to the previous? How does that change in height number 1 compare to change in height number 2 for the same amount of volume of water? If this is a linear function, this is linear, then the change in height will be the same. What kind of rate of change is that? Constant rate of change. For equal changes in volume, we get the consistent change in height. All right, and then in this part, next part of the bottle, same amount of volume, I get a little change in height, same amount of volume again. How do those changes in height compare to each other? Yeah, so this is another constant rate of change, but a different constant rate of change, right? So what kind of bottle, as you put in equal amounts of volume, gives equal changes in height? What would the bottle be like? But no, so what kind of bottle gives you equal changes in height for the same amount of volume put in each time? Yes, vertical sides, right? Vertical sides. So this will be a wide bottle, and this will be narrow here, right? Okay, right. So we're going to start. It's going to start narrow because you're getting large equal changes in height at first. That means a narrow bottle, right? And then what happens right here? So then it gets wider. It gets wider like this. Suddenly, the rate of change is less. Suddenly. So as soon as we get past that amount of volume or that height, so you got to draw it this way. Okay, so again, there's an abrupt change there in the rate. And so then it starts a new constant rate abruptly. So that means suddenly it's wider. And then in this part, what are the changes? How did each change compare with the previous change? Not constant. So be more specific. Those changes in height are increasing. So therefore the rate of change is increasing. There we see that concave up shape again. That means the rate of change is increasing for concave up. And so the bottle is getting wider or narrower if the rate is increasing? Narrower. This is a very common shaped bottle. We all have one, right? Okay. That's what it would look like. Okay, again, let me just emphasize. Take equal changes in the independent, compare resulting changes in the dependent quantity. All right, I'm going to do a different kind of example. Any questions on this? Yeah. Question, yeah. Where? It's pretty close. So you're talking about right here? Yeah, it looks like it maybe goes down abruptly a little bit. So maybe just a little bit out first. Not much. It's almost the same. But yeah, you're right. But I think it's close enough to just assume you're kind of maintaining that rate when you start this new part of the bottle. Other questions? Yeah.
If the sides of the bottle were sloped, would that make it exponential? Like how would you represent that on the graph?
Okay, so the sides are sloped.
Oh, sorry, if they were like.
So they'd have to, so there's all different kinds of ways that we could slope the sides, and we could have curved sides, right? We could have curved like that and curved like this, and those would all be an increasing rate of change. So somewhere in there is a shape of a bottle that would result in exponential growth of the height. I don't know what it is, but there's all different kinds of ways we can get narrower. We can get narrower like a bowl. We can get narrower this way. So which one of those shapes of the bottle results in true exponential growth? I don't know, but it's somewhere. It is. It exists. Other questions? Okay, so quickly here, we're going to do all right, new situation. So this is going to be Mark's distance from the table. No, Mark's time since he started walking. Okay, and then this is going to be the dependent. It's going to be Mark's distance from the front table. Or the counter, or whatever you want to say. Okay? So, this is going to look kind of funny and weird, and that's okay. Every semester. Right. So, we'll start here. And the first quantity is the time since I started walking. Changing quantity, right? It takes on 1 second, 2 seconds, 10 seconds. And then the other quantity is going to be my distance from the table. Okay? So, here we go. Clock starts now. All right, I'll do it again. See me? Ready? Time starts now. Academy Award-winning performance. Okay, here we go. So, time since I started walking, distance from the table. So we started 0, 0, right? Right there, that point. Yes? No, a time equals 0. I have some positive distance from the table. Here we are. Don't care about the numbers right now. What do? We take a small increment of time. Maybe it's a half a second. Maybe it's a second, but a small increment of time, like this. And we say, does my distance from the table in that first unit of time, does it increase, decrease, or stay the same? Decrease. A lot or a little? I started slow, so it's going to just a little bit of decrease. Gives us a point. Same change in time again. Did my distance from the table in the second increment of time, did it increase, decrease, or stay the same? Decreased again. Was the amount of decrease less or greater? Right. Greater, decrease. And that was kind of the first half of this. Every time that unit of time went by, the change was? Okay, here's the problem. What are these changes? Are they negative or positive changes? This is really hard and confusing, okay? So just don't pack up and take off. This takes a lot of practice. These changes, so delta D, the changes in distance, are, first of all, they're negative. Are these changes getting more negative or less negative? They're getting more negative. Do you see that? The changes are negative, and they're getting more negative. When changes get more negative, are those changes increasing or are those changes decreasing? They're getting more negative. This is very hard to grasp. The changes are decreasing. The amount of distance that I cover in each of these times is increasing. I'm covering more distance each time. But the quantity is the distance from the table. And so those changes are negative. Those changes are negative. And changes that get more and more negative are decreasing changes. So if the changes are decreasing, what about the rate of change? Decreasing. Because the rate of change just follows with the changes. And so we have a So the reason we do this is now we have consistent. This is concave down. And concave down means decreasing rate of change. But this is really hard. You got to practice it over and over again. The distance is decreasing and the changes are getting more negative. Therefore, the changes are decreasing as well. So the rate of change, my rate of change was decreasing as in that first part, even though I was speeding up. So if my rate of change of the quantity, this is the table, is decreasing. Then my rate of change right now, if the quantity is this in the table, my rate of change is decreasing. See it right.
You have a question. All right, I do understand why they are negative, but I only get that because it already determined the graph that you had made right here. But going that way because it's going this way down based on the distance. Yeah, that's negative. How do I determine though? How do you determine that your distance is decreasing based on the first and the second time that you did it? Because I think the distance was increasing because even though you didn't start at 0 the first time, the second time you were further away, so the distance would have been an increase.
The amount of distance that I covered was increasing.
Okay.
But the change in the quantity is negative. This is a negative change. That's the whole point.
The fact that because of the fact that you're covering the distance, it's then being negative. That since you're
because the distance is decreasing. So at every change in my distance is a negative change because the distance is decreasing.
Lost me again.
The distance is decreasing. I'm 10 away, I'm 8 away, I'm 6 away, right?
Not per each time you do it, but per
No,
when you're doing it.
The quantity of distance. My distance is decreasing.
Okay.
I'm 9, then I'm 7, then I'm 6, then I'm
Okay.
5. Okay? So those changes from 10 to 8, it's negative 2. From 8 to 6, negative 2. From 6 to 5, negative 1.
Okay.
So my changes are negative. Okay? So if changes are negative and getting more negative, so that like negative 1, negative 2, negative 3, those changes are decreasing.
8 minus 5, wouldn't that still be positive numbers?
No, the distance is 10, and then it's 8, and then it's 6, and then it's 5. So you have a negative 2 change, then a negative 3 change, negative 4. See?
Okay, and then those changes are getting more decreasing.
Those changes are getting more negative, right? So it's like I got 1 foot closer, then I got 2 feet closer, then I got 3 feet closer in each second.
Okay.
So that's like a change of negative 1, change of negative 2, change of negative 3.
Okay.
So is that a decreasing list of numbers or an increasing list of numbers? Why isn't this working?
It's a decreasing list.
Oh, because I unplugged it. It's a decreasing list. Negative 1, negative 2, negative 3. Those numbers are decreasing.
Mm-hmm.
So that's what we mean. The changes are decreasing. They're becoming more negative.
And then therefore the rate of change.
Therefore, the rate of change is decreasing. I'm speeding up, but the quantity is distance from the table. I'm speeding up towards the table. Therefore, my rate of change is decreasing. It's hard.
Okay.